English and okay. So today I want to talk about my research on homological properties of LP spaces, and it's kind of the last report on this subject. I believe I closed the topic here, and this will be the finalizing talk. So let me share my screen. Can you see it?
Well, there are some 3 balls in the written Budapest. And here is something with mathematics. Дорогие коллеги. Lack of metric projectivity. What is? But in my screen it is that's excellent. No, a little bit less, because I do not see what is on the right. Well, maybe. Okay.
So
a little bit less, if it is possible. If not, leave it as it is. Okay. Fine. Please.
So let me remind the notions of homological algebra from our seminar. So we will deal with projectivity, injectivity, and flatness. And the most well-developed and well-known notion is the notion of relative projectivity, injectivity, and flatness. So these notions are defined as follows. We consider a Banach module P, and we consider a class of epimorphisms, and we solve the lifting problem. In other words, we need to find a morphism psi, psi that makes this diagram commutative, and we wish to solve this problem for arbitrary morphism phi. The notion of projectivity essentially depends on the class of admissible epimorphisms, which we allow here. In relative theory, we consider morphisms that have right inverse bounded linear operator. There is a more strict version of projectivity called topological projectivity, where we consider morphisms, epimorphisms that just open maps. And the strictest version of projective model, we call it metrically projective. This notion requires this class of morphisms to be quotient maps that map the closed unit ball onto the closed unit ball. These last 2 versions of projectivity regained attention with the advent of quantum functional analysis, but originally they were developed by Graven as for the metric projectivity, and by White as for the topological version. Similarly, we can define injective modules, but this time we solve extension problems. For each morphism, we need to find phi. We need to find a morphism C that makes this diagram commutative, and we solve these extension problems for a given class of monomorphisms. In case of relative theory, we consider monomorphisms that have left inverse bounded linear operator. For topological injectivity, we consider embeddings, that is, morphisms with closed image. And for metric theory, we consider isometric embeddings. Finally, we can define a notion of flat module for all three theories, and these theories all work the same way. We take a class of monomorphisms that I already defined for the case of injectivity, and we require that tensoring with the identity operator on a given module F keeps the class of keeps the type of the given monomorphism. For example, in the metrically flat module is a module F such that isometric amorphisms turn into isometric monomorphisms. Again, these are the classical definitions injective or flat modules. So the modification requires that we can extend our class of admissible morphisms, and we can consider just embeddings, but we require that the class of extensions or liftings had to have a bound on their norm. So if we give a quantifiable version of the open map, soon I'll give the definition of this quantified version, say it's C topologically surjective morphism, then the lifting has to have the upper norm bound. The norm of the lifting has to be less than the constant C quantifying the epimorphism. Similarly, we can define give a quantitative version of the embedding, and we call such morphism C topologically injective. And similarly, we require that the extension has to have norm less than C. So what are these quantitative versions of open maps and embeddings? We say that the embedding is the C topologically injective if it's bounded below with the constant C to the power -1, or we can just move that constant in front of the norm of the in the image. As for the C topologically surjective operators, then we say then we require that the map is open, and for any vector in the codomain, we can find a vector in the domain that is mapped to the vector y, and we have the following norm inequality for T. These are the quantitative versions of the admissible maps in our theories, and I think I should give a perspective, a list of existing results on these matters. So let's start from the oldest theory, the relative one. Let me add a page here. So for the relative theory, what do we have? I shall consider LP spaces defined on a locally compact space S, endowed with the measure mu. This measure is finite and Borel and regular. Also, I will consider only the reflexive range. So P is strictly greater than 1 and less than infinity. Then these spaces are considered as Banach modules over the algebra of continuous functions vanishing at infinity. What do we know about projectivity in this case? And injectivity and flatness. In fact, the the relative theory, is not very demanding, and LP spaces are always flat and always injective. As for the projectivity, in this case, the measure mu has to be purely atomic, and all atoms has to be isolated points.
Mm-hmm.
That was the relative theory. As for the topological theory, things are not so good, because there is a theorem proved by me maybe 5 years ago that says the following: if we have a Banach module which is reflexive and which is defined over the algebra with specific geometric structure, to be precise, this algebra should be either L infinity or L1 space. These are spaces which locally look like finite dimensional L infinity space or finite dimensional L1 space. So for algebras with such finite dimensional local structure, their reflexive modules are projective, injective, or flat only when they are finite dimensional. So in all these cases, I need to say that the measure mu is purely atomic, and has finitely many atoms. As some of our visitors know, the metric version of projectivity, injectivity, and flatness are even more demanding. So one should expect the same result for metric version of Banach homology. But it turned out that our measure has to have only one atom. So if you want to know whether LP spaces are metrically projective, injective, and flat, the answer is basically never. Only for one super trivial case when there is one atom for our measure. And even though this looks like disappointing result and should be easily proved, it took me a lot of time to come up with the solution, because this solution is inherently finite dimensional argument, and you cannot to appeal to some fancy theorem, infinite dimensionality, and etc. But there is a workaround for the case of Banach modules. So let LP n be a Banach module over L infinity and dimensional, and we consider them as Banach spaces over R. How do we show that LPn is metrically injective if and only if n equals 1? The argument is very simple. Suppose that n is greater than 1. One can show that if our LP space is metrically injective for some n greater than 1, then LP2 will be metrically injective too. So we need to consider only two-dimensional case. Now, when the Banach module is metrically injective, in fact, we need to show that this space is contractively complemented in the following space. Here is the L infinity sum of L1 spaces over some huge index set. For those who are interested, we need to consider the following map, say rho. And this map is defined as follows. The index f runs through the unit ball of the two-dimensional LQ space. And we take a vector from L to P and map it to the following sequence. Where f runs through the unit ball of LQ space. How do we show that this embedding gives a copy of L2P inside this huge space, and this copy is not contractively complemented? The proof is very simple, because for real Banach spaces, we have the following isometric isomorphism. Two-dimensional L1 space is isometric to the two-dimensional L infinity space. And therefore, this space is isometrically isomorphic to the L infinity sum of L infinity spaces. We may not pay attention to the exact structure of this infinity sum and just say that this space is isometrically isomorphic to some L infinity space on some infinite index set, say lambda prime. So the canonical embedding should give us a contractively complemented LP space inside L infinity space. But we know for sure that all contractively complemented subspaces of L infinity space should again be L infinity space. So if L2P is metrically injective, it should be isomorphic to two-dimensional L infinity space, which is not true. This is a cheap proof, but for the case of real Banach spaces. Now, the point of my talk to show the same result for L infinity space for complex Banach spaces. Excuse me?
Complex spaces. Now you will consider.
For the complex Banach spaces.
Yes.
My approach will be quite straightforward, but with a lot of technicalities. The idea is to consider the standard extension problem. We pick an, let me use this ink. We pick an LP space which is n-dimensional. We try to build an extension for the identity map, and we try to build an extension C along the following embedding C F and our idea will be to pick up a specific index set F, which will give us an extension problem which is hard to solve. Later, we will estimate the constant C for this embedding. I want to remind that every embedding has its own constant which quantifies its embedding into the codomain. So we will quantify the constant C. Usually this constant is called cursivity constant, and we shall show that any extension C, excuse me, and we shall show that any extension P has norm greater than the cursivity constant of this embedding. The embedding is defined as follows. We just pick a vector and multiply it by functionals from the units, not the unit. We just multiply this vector by functionals from the LP adjoint. This gives us a list of vectors from the L1 space. Okay, the cursivity constant defined as follows it's just simply a corollary of this definition. Note that for a given embedding, we can put here a lot of different constants, but I want to pick the smallest one. So here is our definition of the cursivity constant, the best one. So how do we estimate, how do we describe these extensions? First, let's consider a simple case. Consider a morphism which acts between two LP spaces, LP and LQ. Note that Q is not the adjoint of P, it's just another number. And all such morphisms are just multiplication maps, multiplication by some bounded sequence. Okay, so we have a full description of morphisms, L infinity morphisms between LP spaces. As for the map C, which acts from this huge space into LP, for the case of finite family F, we can also give a full description. And during my talk, mostly the family F will be finite. In this case, we can represent the map the sum of simpler maps. I'll denote them CF. How do they work? Consider a family of L1 spaces, which added up with infinity norm, and etc. And they composed into one big space, and we act into LP space. Then we can just consider one copy of L1 embedded into our big space, which is this one, and consider the map, not the map C, but the map CF. These are the map of the type given here, so we can have we have a full description of such maps, and since the family F is finite, we can sum up these maps CF and get the full description of the map C. Basically, any extension map C is the sum of multiplication maps. We just need to pick a correct family of bounded sequences eta. So from now on, I'll assume that all maps C are parameterized by family eta of bounded sequences. But these maps are not the maps I'll be interested in. I will not be interested in any such maps, because while solving the extension problem, I need this diagram to be commutative. Therefore, the composition, like this, needs to give an identity map.
Yeah.
So I need to consider this equality and somehow try to extract conditions, required restrictions put on this family eta. And this is quite an easy exercise. You can consider this equality and put in the role of x just the basis vectors of the LP space. That would be enough to give the full list of conditions for the parameterizing family eta. And these conditions are listed here. So this, the family eta need to satisfy this list of equations. I say list because for each index, for each element of the index set lambda, we have such an equation. These equations are connected, are related to the family F, which I have not specified yet. So we are solving this problem for an arbitrary finite family F. But later I'll give a concrete example. At this moment, we now have a full understanding what is the extension of the identity map in this extension problem. The time has come to compute some norms. In this proposition, I give an exact formula for the norm of the operator psi parameterized by the family eta. And the main tool here is the convexity of the LP norm. Here is the definition of the operator norm. We take the supremum over all vectors in the domain with norm less than 1. Since our domain is an L infinity sum, we can write a whole family of inequalities for our vector t. And we can further expand this requirement into the following list. It looks intimidating, but basically you are optimizing over the simplex defined by this equality. And while you optimize over this sequence, over this simplex, you need to look at the norm at the codomain. Since we have an explicit description of the operator psi,
Norbert, I'm sorry to interrupt. The problem is that today we are using a free version of Zoom, and it seems that the time of our session is limited by 40 minutes. So now, if you don't mind, let's finish this conference and then reconnect again by using the same link.
Okay. Okay, I'm leaving now and soon will
be. I didn't understand. Спасибо, Денис, большое.
So right now we need to compute the norm of the extension psi we take the supremum over this simplex, and we take the p norm of the sum of the multiplications by the vectors E with index f. We have this intimidating expression, and one needs to remember that we optimize over the vectors t with two indices, and these vectors are complex, and we need to get rid of this. Let's write these complex numbers in the trigonometric form using their absolute value and their argument. Then we get this expression. Since their argument can be arbitrary, for the maximization of this value, we can choose these arguments in a such way that these values alpha will be equal to the argument of the parameterizing vectors. In this case, we can get rid of these arguments and optimize over absolute values of the vectors t. Now we arrive at purely real valued problem. So we are in the realm of classical convex optimization. And now let's look carefully. We optimize over a simplex, and we optimize this expression. We can write this expression as the p norm of the sum of linear operators. Therefore, the maximum, the supremum of this value is attained at extreme points of this simplex. The extreme points of this simplex.
Чего он там пикал?
So I can continue. Can I continue?
Yes, please.
Okay. We should maximize this convex function, strictly convex function, over this set, and to be more precise, over its extreme points. And extreme points of this set are a family of vectors Rf, where we pick only one coordinate lambda, where this vector has a non-zero value. In a formal way, we can say that the vector R corresponding to the elements f of the family f script at coordinate lambda had to be a delta function at a specific index which depends on the vector f. Given this description of extreme points of the simplex C, we get this expression. Even though it doesn't look very simple for the analysis, it's a finite expression because we assume that the index set is finite and the family F is also finite. So here we take a maximum over a finite family, but a family could be quite huge because this is the indexing of this expression goes along all possible functions from f to lambda. Okay, so at this moment we have a full understanding of all possible extensions in this problem. We know the explicit formula for the norm of the extension and the explicit formula for the action of this operator and the requirement for the family eta describing this extension. Now we need to remember that for the case of metric injectivity, the extension has to have norm less than C, and C is the cursivity constant for the embedding C. Now the time has come to analyze the cursivity constant of the embedding Xi. I will not give the expression for the cursivity constant for an arbitrary family F script. From now on, I'll consider a specific family. This family defined as follows, but to get an understanding, let's consider a simple case where lambda has two elements. Basically, I consider a family inside L2 P adjoint. And this family parameterized with the value kappa looks like this. I pick one basis vector, E2, I pick another basis vector, E1, and I pick this small vector, say E star. And the size of this vector is controlled by this constant. I believe listeners can guess how this construction works for the case of bigger index sets. So from now on, I will estimate the cursivity constant for this type of families F. And the construction goes the same way. We pick the definition. In this definition, we maximize the LP norm over some strange condition. But if you recall the explicit formula for the map C, you get that this requirement is equivalent to the list of the following inequalities. These inequalities, even though they go over all complex vectors, these inequalities always use the absolute value of the coordinates of the vector. So we can reduce this problem to the real valued case. And in this real valued case, we again have a maximization of the strictly convex function over some simplex. This simplex is not so simple as in the previous case. And to give a brief idea how it looks like, this kind of simplex in the two-dimensional case, in the case where index set is has two elements, the simplex looks like this. So it's a square with the corners being cut. And in this case, our simplex has 8 extreme points. So the maximum of this strictly convex function is attained at such points. Luckily, the value of LP norm at all these points is the same, and it equals this expression. From now on, our goal was to show that the norm of all possible extensions are greater than the cursivity constant of the embedding C. So we need to show that this humongous expression is always greater than this one. During my research, I just wrote a program that analyzes this function for some specific cases. It turned out that we can estimate this kind of norms from below. And I'll call this constant, this estimate from below, by nu. Excuse me, here is the exact definition. Let me find it. Yeah, this is the definition of the lower bound of all possible extensions of the identity map. Recall that we are looking for the extensions of the identity map, and the infimum of their norm I'll denote as nu. So from now on, I'll estimate from below this constant, but for the specific family F, this one. This estimate looks like this. How do we get this estimate? First of all, this constant is an infimum not over all possible norms of extensions, but the extensions that are make our diagram commutative. This condition puts a restriction on the family eta that parameterizes extensions psi. Well, when we pick this infimum, we get the following equations for the parameterizing vector family eta. And now we need to recall the formula for the norm of the extension. Look at this formula. We take maximum over all functions from the family F to the index set lambda. By computer analysis, by numerical experiment, I found that we can restrict our considerations and not pick all possible functions, but functions of this form. If we restrict our family of functions D, we get a smaller maximum, but in this case, our expression, which we take maximum of, become a little bit simpler. It's simpler because we don't have a double sum here. Okay, then we shall use our requirement that the parameterizing family eta has to satisfy the condition that the diagram is commutative. Basically, we get rid of this expression. It becomes a little more complex, and it's a pun because eta is a complex value. And again, I want to get rid of this. This expression can be estimated from below using the inverse triangle inequality, like this one. And from now on, you can see that I pick the absolute value of all these complex numbers eta. Therefore, again, we arrive at convex optimization problem in the real valued case. Basically, I need to find the minimum of this function. To do this, I denote each such expression as alpha I, and the maximum of all this expression as the function alpha. And the intuition is that for convex functions which does not change under the permutation of arguments, their supremum, their infimum is attained at points where all coordinates are equal. And this paragraph, these two paragraphs, explain this idea in detail. I'll skip it. So we, in practice, we do not optimize this function. We optimize the function like this, but with all arguments ti being equal. Basically, we optimize this function of one variable. This is an easy exercise for the first year students to find the infimum of this function. The infimum is attained at this point. Now we plug this expression here and get the infimum. This big expression is the estimate from below for the constant nu. So from now on, we know that the norm of all possible extensions are at least like this. On the other hand, we know that the cursivity constant for embedding C is exactly this expression. If I manage to prove that this constant is strictly less than this constant, then we are done, because we will show that all possible extensions C has norm greater than the cursivity constant of Xi. How do we prove this crazy inequality? We need to show this. If you rearrange the terms, you will arrive at the following expression. It looks like a Hölderlin inequality, but it is not. In fact, we need to use Lyapunov's inequality. It's a specific example of it. The proof is quite simple for this inequality. The only small detail that we need to know when this inequality becomes an equality. It becomes an equality if all coordinates of the vector x are equal. Given that knowledge, to prove this inequality, we consider two vectors. First, we consider vector x with these coordinates, with the parameter r being p. So we pick this data and we plug it into this inequality. We do the same, but for another vector x with another parameter r, and again get another inequality. So given these two inequalities, we multiply them, and miraculously on the right side we get this expression. So we have proved this inequality, we have proved this estimate, therefore we have shown that all possible extensions have norm greater than we expect in the metric injectivity case. We can finalize this result in a fancy way. We can say that any LP space on a finite index set lambda considered as L infinity module is not metrically injective. Is not metrically injective unless the index set has one element or empty. This solves the finite dimensional case for injectivity, but the projectivity and flatness are easily solved too. Why so? Suppose that LP space is metrically flat. Then it is well known for the visitors of our seminar that the adjoint Banach module LP lambda star, which is isomorphic to LP star lambda, has to be injective. But we know that this implies that the index set lambda has to be very small. So LP spaces, finite dimensional LP spaces on an index set are not metrically flat either. And we know that metric projectivity always implies metric flatness. Therefore, we have the same strict constraint for the metrically projective LP spaces. All these considerations were for the LP spaces defined on an index set. Index set can be regarded as the measure space, but for the counting measure. And the rest of the talk is about reducing our general case of measured spaces to this one. I'll skip this part because it's not very exciting. The main technicality here is that in general measure spaces, atoms has not to be singletons. So you can have a big set, maybe an infinite set, which from the point of view of the measure is just an atom. I'll give just two main results here, which give us the reduction. Maybe I will not. So the reduction goes as follows. Suppose that an LP space is metrically injective. And this LP space is considered over a locally compact space with Borel measure mu, which may be assumed even just decomposable. Yeah. Even if mu is decomposable, the result still holds true. And we consider this space as the Banach module over the space of continuous functions vanishing at infinity. Well, if such space is metrically injective, it must be finite dimensional. This result were proved a long time ago by me, and it appeals to the local structure of the algebra. As I said in the beginning of the talk, if our algebra has L infinity type, basically if our algebra on the finite dimensional level looks like L infinity m, then all metrically injective modules over this algebra, reflexive metrically injective modules, has to be finite dimensional. And if LP space is finite dimensional, then the underlying measure has to be purely atomic with finitely many atoms. And then I just reduce the case of general measures with finitely many atoms to the case of LP spaces defined on the index set lambda. And this completely solves the problem of metric injectivity of LP spaces. And by the argument that I gave in the beginning of the talk, we can say that LP spaces are not metrically projective or flat either. From my statement in the beginning, it may seem that having a single atom is necessary and sufficient condition to be metrically flat. In fact, even having one single atom is not enough, because this atom has to be an isolated point. Only in that case, we have a criterion. So metric injectivity, projectivity, and flatness of LP spaces is equivalent to having one single atom, which is an isolated point. A super rare and boring case. So that's it. That's all I wanted to tell you today. I think the most interesting part of the talk is the ability to compute explicit norms of the extensions of the operators and the proof of this crazy inequality.
Yeah, but it's the long and tricky business, in my opinion. But you succeeded. Okay, thank you very much. It was indeed interesting and, in a sense, unusual for our preliminary conversations, results, and Banach homology, etc. Now, honest calculations, a lot of them.
Yeah,
It's
it's an analytic paper.
Yeah. So, what are questions? Casey, do you have? No, Casey is silent.
Well, I wonder if the image of the mapping embedding would be complemented. Is it possible to simplify your estimations or to get something easier? I mean, when it's a standard case, your estimation would be easier, right? Or will be trivial somehow.
What do you mean for the standard case? You mean,
well, for example, yeah, image of psi f by somehow complemented there, and then it should be easier, right? As I guess.
The image of psi in this case is always complemented because I embed a finite-dimensional space.
Oh, yeah, that's fine. Yes.
So
Okay,
the main deal here is norm estimates, because on the algebraic level it works just fine. And the question was about metric injectivity. For example, LP space, finite dimensional LP spaces are always topologically injective, because topological injectivity does not require strict conditions on the norm of the extension.
Yeah, I got it, yes. Mm-hmm.
Okay. Other questions? So people are, yes, silent. They are impressed.
I have a little comment, if you don't mind, in Russian.
Yes.
So at the very beginning, you said that that your talk is kind of a final point in your research project of metric properties of LP spaces. So I recall the following story. I'll tell it in Russian, if you don't mind. Что однажды, когда-то одного известного поэта спросили, уж не помню кого, чем он занимался в последнее время, он сказал, ну, написал стихотворение о любви, закрыл тему.
Ну это известный человек по фамилии Островой. Вот, известный. Это как раз как доказательство его глупости приводилось. Вот.
А тут, собственно, ситуация противоположная.
Да, тут противоположно.
Здесь действительно последняя большая жирная точка.
Да. Хорошо. So, thank you very much again for a very interesting talk. And our next speaker after a week, Dr. Renat Gumerov, and I hope soon professor, or what is, he knows better the situation. So we shall, with pleasure, hear him. So it will be 24th of November. Okay. So after a week, we meet again, to mutual pleasure. Bye-bye.